Solids exist in different shapes and sizes. The molecules within a solid body occupy fixed positions and their relative distance of separation remains constant. The molecules are in equilibrium with each other and experience no net force. The graph displays the intermolecular force between two molecules as the distance of separation between them changes. When molecules are at the equilibrium distance of separation, there is no net force between them. If they come closer than this, they experience mutually repulsive forces. The force becomes mutually attractive when the distance of separation is more than the equilibrium value. What happens when a body is subjected to an external force? The body accelerates in the direction of the net force according to Newton's second law of motion. If a body has a set of two equal and opposite forces acting on it, the net force is zero. In such a case, even though the body does not experience any net force or acceleration, the applied forces deform the body by changing either the shape or size of the object or both. When a body is deformed, the distances of separation between its particles changes from their equilibrium values. This change in intermolecular distance generates intermolecular forces. The distance of separation having increased from the equilibrium value, the molecules experience mutually attractive forces. When the deforming forces are removed, these intermolecular forces try to restore the body to its original shape and size. This property of a body, by virtue of which it regains or tries to regain its original shape and size when deforming forces are removed, is called elasticity. The material is called an elastic material. There are some materials that offer little or no tendency to regain their original shape and size even when deforming forces are removed. Such materials are called plastic, and this property is called plasticity. Putty and mud are almost perfectly plastic. A body can be deformed in one or more of three possible ways, namely longitudinal deformation, volume or bulk deformation, and deformation in shape. If two equal and opposite forces are applied perpendicularly to opposite faces of a body, the length of the body along the line of action of the forces changes. The length will increase for outward forces and decrease for inward or compressive forces. If forces are uniformly applied in all directions on a body, the dimensions of the body undergo an overall change, leading to an increase or decrease in the volume of the body without altering its shape. If two equal and opposite forces act parallel to two opposite faces of a body in a tangential direction to the surfaces as shown, the shape of the body gets distorted. Based on the way in which deforming forces act on a body, the length, volume, or shape of a body changes. When a body is deformed, the intermolecular distance of separation changes from its equilibrium value. This causes intermolecular forces to be generated, which try to restore the body to its original state once the deforming external forces are removed. The sum total of intermolecular restoring forces per unit area is called stress. Stress is measured as the deforming force applied per unit area. If F is the force applied on the surface of a body with an area A. Then, stress is equal to force F by area A. Stress has units of 1 Newton per meter square, which is also called 1 Pascal. Its dimensional formula is ml to power minus 1 T to power minus 2. The fractional deformation produced in the body by the external deforming forces is called strain. It is calculated as the ratio of the change in the body's dimension to the original value of the same dimension. For example, if the original length of a rubber band is L and the increase in its length is delta L, then the strain is equal to the ratio delta L to L. As strain is the ratio of two similar quantities, it has no units. Thus, strain is a dimensionless quantity. A body can be deformed in one or more of three possible ways, namely longitudinal deformation, volume or bulk deformation, and deformation in shape. Based on the manner in which deforming external forces are applied and deform a body, we define three different types of stress and strain. When deforming forces are a pair of equal and opposite outward forces, applied normal to a pair of opposite end faces of a rod, the length of the rod increases, and the stress generated is called tensile stress. When the deforming forces are a pair of equal and opposite inward forces, applied normal to a pair of opposite end faces of a rod, the length of the rod decreases, and the stress generated is called compressive stress. Inward or outward deforming forces applied along the length of a body causes a change in its length. The change in length causes tensile stress or compressive stress, and these are collectively called longitudinal stress. Longitudinal stress is measured as the ratio of the applied force F to the area of the face A. If the length of the rod L changes by delta L, the fractional deformation, called the longitudinal strain, is equal to the ratio of delta L to L. When deforming forces are applied perpendicularly to a body's surface at every point, the volume of a body changes, and the stress generated is called bulk stress or volume stress. Forces acting perpendicularly inward at each point on the surface of a body are equivalent to a uniform increase in external pressure. Therefore, bulk stress is defined as a change in pressure delta P. If the volume of a body V changes by delta V, then the fractional deformation, also called the bulk strain or volume strain, is equal to the ratio of delta V to V. If two equal and opposite forces act parallel to two opposite faces of a body, the shape of the body is distorted. When the deforming forces are a pair of equal and opposite forces applied tangentially to a pair of opposite end faces of a body, the shape of the body is distorted, and the stress generated is called tangential stress or shear stress. Shear stress is measured as the applied tangential force F divided by the area of the face A. When a force is applied to the top surface of the body tangential to it, the top surface is displaced laterally with respect to the bottom surface by length dx. Simultaneously, the vertical face of a body normal to the direction of the force applied is tilted through an angle gamma from the vertical. If the vertical height between the two horizontal surfaces is h, then using the geometry of the right triangle, we get the trigonometric ratio tan gamma is equal to dx by h. For small angles, the value of tan gamma is nearly equal to gamma, and hence, for practical purposes, we consider gamma equal to dx by h. This gamma is the shear strain of the material of the body and is expressed in radian. The dimension perpendicular to the faces under the action of deforming forces rotates through a small angle gamma. The shear strain is equal to the value of gamma expressed in radians. Robert Hooke found that for most materials, for small values of strain, the stress is directly proportional to the strain. Thus, we have stress is equal to K into strain, where K is the constant of proportionality called elastic modulus of the material. If on increasing the stress, the strain is increased beyond a certain value, the proportionality between stress and strain is lost. There are some materials that do not obey Hooke's law. For example, for materials such as polymers like rubber, human muscles, and blood vessels, stress is not proportional to the strain. The relationship between stress and strain of a deformed body depends on the material of the body. The actual stress-strain graph for a body depends on many factors, such as its material, its temperature, and whether it has previously undergone any deformation. The way in which strain changes with stress for any material can be studied experimentally. The corresponding values of stress and strain can be then plotted on a graph. This graph is called the stress-strain curve. In a typical experiment to study the relationship between tensile stress and strain, the material in the shape of a rod or wire is held fixed at one end. The other end of the rod is subjected to a load, which is increased in stages. The elongation of the rod is measured at each stage. A machine used for stress testing is shown on the screen. The two ends of the rod are held between the top and bottom grips. One end is fixed and the other end is pulled to apply a precise load. The stress is calculated by dividing the load F by the original area of cross-section A of the rod. The strain is calculated by dividing the elongation delta L by the original length L of the rod. A typical stress-strain graph is shown. In the initial part of the graph, for low values of strain, the stress-strain curve is a straight line. In this straight line region of the graph from O to A, stress is directly proportional to the strain and Hooke's law is obeyed. Point A is called the proportional limit. As the strain increases further, the graph no longer remains a straight line. However, in the region of the graph between points O and B, if the load is removed at any point, the body completely regains its original length. Point B on the graph is called the elastic limit. The stress corresponding to elastic limit is the maximum stress the substance can withstand and without any residual strain when the load is removed. Beyond the elastic limit B, the strain increases at a faster rate than stress, shown on the graph between points B and D. Even if the load is removed, the substance does not completely regain its original size. The deformation is now called plastic deformation. The value of the stress at point B is called yield strength because this is the minimum stress required to induce plastic deformation. Yield stress is denoted by the symbol SY. So, point B is also called the yield point. The amount of residual strain that remains on removing the load can be determined from the stress-strain curve. For example, if the load is reduced to 0 from point C, the residual strain can be found by drawing a line parallel to OA at C. The point where this line intersects the strain axis gives the residual strain or permanent set. The stress now increases with strain, but less rapidly. The material experiences maximum stress at point D. The value of stress at this point is called tensile stress or breaking stress and is denoted by the symbol SU. It is also referred to as ultimate tensile strength. The stress is not uniform throughout the material. At a point in the material where there is a defect or weakness, all further plastic deformation is concentrated in this region, and the material begins to neck or thin locally. Because the area of cross-section now decreases very rapidly at the neck, the effective load at this point decreases, and so stress reduces till the material actually breaks or fractures at this point. The break point or fracture point is represented by point E on the graph. The stress-strain curve for different materials is different. For example, the stress-strain curve for mild steel and cast iron look different. The curve for concrete and cast iron shows no plastic deformation. This means that they are brittle and will break suddenly at the point of maximum stress. Mild steel experiences large strains for very little change in stress in the plastic region. Such materials have high ductility. So we can say that materials that strain by large amounts before fracturing are ductile, whereas those that rupture at low values of strain are brittle. Accordingly, the study of stress-strain curves for different materials can help scientists identify appropriate material to be used in the design of engineering structures.